This is video 2 on double replacement reactions, and I just want to get through maybe like 4 more examples of how things go and some things to watch for and whatever else. The idea, as we looked at double replacement reactions previously, was that we can predict whether or not they're going to take place by looking for a net ionic equation. And that net ionic equation is what you have, the actual reaction, after removing the things that aren't involved, the spectator ions, that remain unchanged from reactants to products. And we know what ions we have because we took the complete and balanced chemical equation, used the solubility rules to determine phases, and then dissociated everything that was aqueous. We separate everything that's aqueous. So our goal is to complete it and balance it, and then show what's actually reacting, what the actual reaction we have. And that's, again, not something that's intuitive. I don't think it's intuitive that some reactions don't happen, and I don't think it's intuitive that only some of the stuff could react. But that's what we see in some of these, well, in all of these double replacement reactions. We're limited to those 2 scenarios. So our first example, just to warm up again, is a reaction that we do in a lab, a quantitative lab. We do some stoichiometry with it. But that's the reaction of calcium chloride, and we'll leave room for our phases, and sodium carbonate. Okay. Once again, important skill completing and recognizing reaction types. As you look at this reaction, metal and nonmetal, metal and polyatomic ion, both of these indicating you have 2 ionic compounds. It's most likely a double replacement reaction. And if it is, then we need to consider switching the places, right? Replacing cations with cations or anions with anions. And again, unlike single replacement, where we had something by itself replacing something in a compound, here we've got 2 things in compounds, and we're going to assume that they switch places and see if either of those new things is actually new, or if it's just more ions floating around in the solution. To get our products on the other side, one of my sodium, we can take the sodium first. Sodium's a 1+. With the chlorine now, that's a 1-, right? And we crisscross and reduce, and we have NaCl table salt, right? I think it's super duper important to mention, and I keep mentioning it over and over and over. There's a 2 there, but there isn't a 2 there. And the reason for that is we've gotten our formula for the new thing by crisscrossing and reducing. If you look over here, this 2 is there because calcium's a 2+. This 1 that I didn't write there is a 1 because sodium's a 1+. This 2 is a 2 because carbonate is a 2-, and this 1 is a 1 because chloride is a 1-. So hopefully you get tired of hearing me say it and then you don't make that mistake. We've got calcium now, which is a 2+, and carbonate, which is a 2-. And so you could bring the 2 and the 2 down, and then you have to remember not only are we crisscrossing, but we are also reducing. All right, now we said we're going to identify those phases using our solubility rules. I don't know what my dogs just did in the background, but hopefully it's nothing permanent. If we look here, my general idea was to say, do I have anything with a nitrate? No nitrates. All right, do I have anything with a group 1 metal? Well, group 1 metals, there's sodium, right? So if it has a group 1 metal, we're going to declare it is aqueous. It is soluble, and it will dissociate. There's not actually any sodium carbonate in this solution. I've got sodium ions and carbonate ions floating around. And a lot of people don't realize that. Like, if you have salt water, you don't have salt in the water. You have sodium ions and chloride ions that have separated from each other, right? If you have sugar water, you have separate sugar molecules floating around. There is sugar in sugar water. There isn't salt in salt water. The NaCl has dissociated into its ions. Anyway, aqueous dissociates. All right, over here I've got my group 1 metal again, so that's going to be aqueous. And then I need to worry about other stuff. So I address the nitrates, I address the group 1 metals. Do I have any chlorides, bromides, or iodides? Yes, there's a chloride right there. Is it with silver, mercury, or lead? No, then this is going to be aqueous, all right? And if all of those words went by super quickly in slow-mo, chlorides, bromides, and iodides will be aqueous, as long as they're not with silver, mercury, or lead, and it's not. Then we get to this side. This rule didn't cover it, this rule didn't cover it, this rule didn't cover it. I need to find a rule about calciums or carbonates. And these rules are based on, for the most part, anions, except for that first rule. So I'll look for carbonates, right? Aha, there's carbonates. And it says they're going to be insoluble unless you have a group 1 metal or ammonium, and we don't. All right, so once again, carbonates insoluble, so I'm going to put solid. That is a critical step in doing these problems. We completed it. We haven't balanced it, but we did add phases. We should probably take a moment to balance this. I'll do that over here. We have calcium, chlorine, sodium, and carbonate. And again, for balancing purposes, if you have a polyatomic ion that's on both sides, keep it together. It's easier to balance. All right, 1, 2, 2, 1. On the product side, 1, 1, 1, 1. So it looks like we can put a 2 there, and it will be balanced. And again, anybody can look at that work and know it's balanced, excuse me. This is a step that I declared in the last video. This isn't really something you have to do, but I find it to be very useful in keeping track of things, okay? So if we look here, I've got calcium. That is a thing that I have. And I have chlorine. It is not a polyatomic ion, so this 2 is not part of it, all right? Carbonate is a polyatomic ion, so that 3 is part of it, right? Carbonate is a polyatomic ion, the 3 is part of it. Chlorine is not a polyatomic ion, or chloride, so that 2 is not part of it. Sodium is not a polyatomic ion, so the 2 is not part of it. Sodium and chlorine, right? And that 2 right here will apply. Calcium and carbonate, I have one piece. When we were talking about dissociating, we said we would dissociate aqueous species. That's not aqueous, so I'm not going to break it apart. Aqueous, 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 by our solubility rules. I do want to mention right here, this 2 applies to both the sodium and the chloride as we break things apart. Just because it's an amusing game to me. Let's see if I can predict the spacing on these. Now I'm just cheating by making sure I have the space. All right, so let's split this apart into its pieces. Key things to watch for. You got to have your charges, you got to have your phases. And I'll say that again. You must have your charges and you must have your phases when you split these things apart. Okay? And if you're saying, well, why? The answer is this is calcium ions and chloride ions forming an ionic compound. So when we break things apart, we have to represent them as ions. Okay? So we've got calcium, 2+, aqueous. How do I know? Well, that aqueous goes there. It is calcium 2+, all right? And I've got 2 chloride ions. And I know it's 2 chloride ions because I have 2 minus things to balance out the 2+ from that calcium. It is not diatomic chlorine because diatomic chlorine wouldn't be in a compound. Yeah, I've never thought of saying it that way. This is part of a compound. It's not diatomic chlorine because diatomic chlorine is its own compound. All right, I'm not upset with how that turned out. We've got 2 sodium ions, and we've got 1 carbonate ion. That is that side. I have 2 sodium ions, and 2 also applies to the chlorides, 2 chloride ions, and whatever's left, which is our calcium carbonate. And again, the reason I did not dissociate it is because it's not aqueous, it's a solid, all right? So that's a very important factor right there. We need to identify our spectator ions so we can write our net ionic equation. As a little refresher from last time, do you need these charges? Yes. How important is it? Life or death, okay? Sodium ions, you'd be dead without them. That's part of the sodium-potassium pumps. That's how your muscles work. Sodium metal would kill you. You'd die without it, it would kill you. You'd die without it, it would kill you, all right? That's how important they are. So make sure that those charges are showing up. Obviously, highlighting those charges is not part of the answer, but I want it jumping out of the page at you. And then we need those phases as well, and the phases just carry down, so there's nothing suspicious going on there. I'm going to cross out my spectators with a better color than last time. So as we look here, we said that our spectator ions were going to be any species that remain unchanged from reactant side to product side, okay? So if we look here, calcium ions, take a picture in your mind of what that looks like. No, that's calcium in a compound. It's not calcium ions, all right? So this is different than this, then it is not a spectator, right? Chloride ions, spectator, okay? Sodium ions, spectator. Carbonate ions, part of a compound, not a spectator, okay? So the spectators are the things that are unchanged. They're just there balancing charge. They're not involved in the actual reaction. But our calcium ions and our carbonate ions are forming that calcium carbonate. So let's write that out and then see what we can do. We have Ca2 plus, aqueous, and our carbonate, CO3 2 minus, and that's giving us our calcium carbonate, solid. All right, that is our answer. We do have a reaction taking place, and that's it. The sodium ions and the chloride ions are floating around doing nothing in the beginning except balancing charge, and floating around doing nothing in the end except balancing charge. So there's a typical type of double replacement reaction. There's no change in oxidation states. It's not redox, so it is different from our 4 other reaction types, which are all oxidation reduction variations. This is different, okay? Our next example is going to be a variation, and a kind of important variation of a double replacement reaction. And we're going to pick something simple here like HCl, aqueous hydrochloric, spoiler alert, aqueous hydrochloric acid, and sodium hydroxide. Okay, HCl is a strong acid. NaOH is a strong base. I'll put that there, and I'll draw my arrow. As we look at it, ionic compounds, we're expecting then to do some substitution here, displacing one with the other. Okay, so the sodium and the hydrogen are going to switch places. So now my sodium is going to be with the chlorine. And the way I know that formula is to crisscross and reduce, all right? Na is a 1 plus, and Cl is a 1 minus, so that's its formula, right? And I'm going to put that right there. And then I've got hydrogen now with hydroxide, okay? Hydrogen's a 1 plus, hydroxide is a 1 minus. You can't see it, but I'm laughing because HOH is water, right? It's actually a little easier to balance if we leave it as HOH, but it certainly wouldn't hurt to put it as H2O. And we do need to leave room for our phases there. Okay, so that's where we are on that one. Let us balance it, and then we can fill in the phases and see where things go from there. We've got hydrogen, chlorine, sodium, and hydroxide. And again, you don't have to leave the hydroxide together, but it'll make our lives a little easier, and looks balanced to me. There we go. You might even, at that point in time, just rewrite that as H2O. There'd be no problem with that. So, okay, and there's something we're going to do with that H2O. We need to assign those phases. We know what those phases are based on our solubility rules. I let slip that the HCl is aqueous, but you would have known that because chlorides are soluble as long as they're not with silver, mercury, or lead. So chloride is with hydrogen. That's not silver, mercury, or lead. We're going to treat it as a compound that will be aqueous. We've got sodium and hydroxide. Sodium is a group 1 metal, so this is going to be aqueous. On this side, I have the sodium, which is a group 1 metal, which would tell us it's aqueous. Or I have the chloride without silver, mercury, or lead, so either of those things would tell us it's aqueous. And then we have water. Water can't be aqueous because that would be in water, and water is water, right? So when you have H2O, it's not aqueous, it is liquid in these situations. And that is a super, super, super important thing. Important enough that I'm going to highlight it, right? Something has changed, it's not aqueous. Okay, that didn't hold up well, but we can work with it. Now we're going to dissociate all of our aqueous species, right? We have the completed balanced chemical equation. We need to get a complete ionic equation, and we're going to do that by dissociating our species, right? Our pieces of our electrolytes, yeah? And I'm not going to dissociate that because it's not aqueous. So I'm not going to draw the arrows this time. We can just move on with our lives. I've got hydrogen ions. Those are aqueous, right? I've got chloride ions. Those are aqueous, okay? And just so we're clear, the hydrogen is a 1 plus, the chlorine, the chloride is a 1 minus. So when I separate them, I have to put the plus and the minus. The reason I don't see anything right here is because 1 plus and 1 minus cancel out to 0, okay? No charge here because the pieces have charges that cancel out, and we need to show those charges down there, all right? We've got sodium ions and hydroxide ions. And that's going to give us sodium ions and chloride ions and water. and that water is a liquid. All right, super important stuff going on. We're going to look for spectators as we did up here. Spectators will remain unchanged from reactants to products. Hydrogen ions, those are not hydrogen ions. It's part of a compound, so this must be part of our actual chemical reaction. Chloride ions, that is a spectator, right? Sodium ions is part of our spectator, and hydroxide is part of that. So that is my actual reaction that's taking place. The sodium ions the hydrogen ions plus the hydroxide ions making water. So we have H plus and OH minus. That's giving us H2O. Okay, so I can box that in or whatever, that's our answer. So this is our net ionic equation, and it happens to be the same net ionic equation for all acid-base neutralizations, okay? So this happens to be the net ionic equation for all strong acid-base neutralizations. All right. And what we mean by neutralization, this terminology is kind of important. A neutralization is when you have stoichiometrically equal amounts of acid and base, all right? So you have exactly how much acid you need to react with all of the base so that they cancel out, we'll say. So anyway, this is the same net ionic equation for all of those acid-base neutralizations. All right, we'll see if we can get a few more examples here, at least two anyway. And let's try something that looks a little scarier. In fact, I think this is awesome because it looks double scary. That's why I chose this. That is the ammonium polyatomic ion. And we're going to need two of them because we're going to attach it to the oxalate C2O4 polyatomic ion. Okay? And I'm going to mix that into a beaker with potassium acetate, CH3COO. All right, we're going to put our parenthesis right there. Right off the bat, this is terrifying, right? Like step one, panic. Okay, I'm still there, and I'm still there. But the key is recognizing your pieces, and a skill you cannot escape is being able to spot your polyatomic ions, all right? That's what's going to get you out of a disaster, being able to recognize them when they appear. So if you look here, you can say to yourself, okay, NH4, that is a polyatomic ion, and I have two of them. C2O4 is a polyatomic ion. It is the oxalate polyatomic ion, and I have one of them. Potassium is an ion, and Chku, the acetate polyatomic ion, is that. And you might also see that as C2H3O2. I think in one of the stoichiometry videos, I talked about why we often write it as CH3COO as opposed to C2H3O2. Okay? Those are our pieces. So as we get to the other side, we're going to say what we did before, which is maybe cations or anions are switching places. And let's see what we get for our new products. The potassium is now going to be with the oxalate. That's a 1 plus and a 2 minus, so we're going to need two of those potassiums. And here, you may be saying to yourself, like, why can't we reduce? Why can't I make this like NH4CO2 or something? And the answer is because this is something and I have one of it. If I had two of them or four of them, I could reduce here. But this is something. You don't even know necessarily that it's a C2O4. I have one of whatever's under my finger, right? I have one of whatever I'm hiding there, and it's not going to reduce when you have a 1 and a 2, okay? We'll leave room for our phases right there. And our other product. And now we have the ammonium with the acetate. Ammonium is an NH4, and it's a 1 plus. And our acetate is the CH3COO, and that's a 1 minus. And we'll put our parenthesis right there, and we're ready to go. So first up, looks super scary, but you have to get over how scary it looks by spotting your polyatomic ions. Rely on that identification. And then you can break it down into those same pieces on the other side. I have this potassium piece, and I have oxalate, and I have ammonium, and I have acetate. Now this is not balanced as written, so I'm going to have to do some balancing, I guess. Maybe I'll do my balancing up here. We have ammonium and oxalate, potassium, and acetate. 2, 1, 1, 1, right? Product side, I have 2 potassiums and 1, 1, 1. So we're going to have to fix the ammoniums on the product side. We can put a 2 right there. That fixes it, but it screws up the acetates. But that's okay, because if I put a 2 right there, it will fix both my potassiums and my acetates in one fell swoop. Okay, we need to add some phases. We will use our solubility rules to do that. And again, the things that I check for right off the bat, nitrates. I don't see any, right? NO3 minus isn't there. Do I have any group 1 metals? Potassium. Potassium is a group 1 metal, so whatever has the potassium is going to be aqueous. Whatever has the potassium is going to be aqueous. And then check for chlorides, bromides, and iodides. No, 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 no. And then you're going to have to check for other rules. Well, this is a pretty important rule right here, this NH4+, and I've got one. So that has to be aqueous, right? If it has that NH4+, it's soluble. If it has that NH4+, it's soluble. Okay? Spoiler alert, aqueous, 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 ions, 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 nothing's changing. There's going to be no reaction here after we break things apart into the net ionic equation, or sorry, the complete ionic equation, and look for a net ionic equation. All right, so let's split things apart. I have ammonium ions. In fact, I have 2 of them, right? And that's aqueous. I have oxalate, C2O4, aqueous. 2 potassium ions, those are aqueous. And 2 acetates, Chku. This is going to give us our 2 potassium ions. And oxalate, C2O4, 2 minus. And 2 ammoniums and 2 acetates. You can often catch, if you balanced incorrectly, if things don't match up down here. So just keep an eye on that. It's kind of a fail-safe in terms of is it balanced or not. Do you need the charges? Yes, life or death, right? So let's look for our spectators. Our spectators should remain unchanged from left to right. We'll look if we have any ammoniums. Yes, we do. We will look if we have any oxalates. Yes, we do. Do we have any potassium ions? Yes, we do. And do we have any acetates? Yes, we do. Okay. So in the beginning, I would have a beaker with some ions, and I would have another beaker with some ions, and in the end, I'd have a beaker with all those ions. There's nothing happening here. There's no net ionic equation. So let's take note of that. Looking for brown marker. All right. So there's no net ionic equation. Therefore, there's no reaction. Okay. So you do need an explanation. If you were to put no reaction, that could be true, right? But now you're giving an explanation. There's no reaction because there's no net ionic equation. All right. I'm going to make an unwise decision and try and squeeze in one more example on this side, and then maybe we can fit one in there as a last example. Got my solubility rules. Let's try iron chlorate, iron 3 chlorate, reacting with rubidium sulfide. And the way I would get these formulas, if we needed to, is I would crisscross and reduce. Iron 3, the 3 goes there. Chlorate's a 1 minus, it goes there. Rubidium's a 1 plus, sulfide is a 1 minus. So we look at it. We've got 2 ionic compounds, metal and polyatomic ion, metal and nonmetal. So we're expecting it to be double replacement. That means we're going to do things switch places. We've got the iron and the rubidium. What we would get then is iron with our sulfide, and the iron was a 3 plus, and the sulfur was a 2 minus. So there would be a 2 there and a 3 there. My children are running around upstairs, if you can hear that. Okay? Iron sulfide is iron pyrite very often, which is fool's gold. So it's often found near actual gold deposits. Rubidium now goes with that chlorate. Rubidium is a 1+. Chlorate is a 1-, and so that is okay as written. We'll put our parenthesis right there. We do need to balance it. So we'll set up our table of reactants and products. We have iron, ClO3, rubidium, and sulfur. 1, 3, 2, 1. All right. Then on the product side, we have 2 irons, 3 sulfurs, 1 rubidium, and 1 chlorate. It's not balanced, in case you didn't notice. We're going to have a way here to get 1 sulfur and 1 iron to turn into 2 sulfurs and 2 irons and 3 sulfurs. So I think you can predict we're probably going to have 6 involved in one way or another. And that's going to, we'll try this first for our irons. Fixes that, gives us 6 chlorates. And then we're going to try and maybe fix the chlorates on the other side. So I'll put a 6. And that fixes that, but now we have 6 rubidiums, so maybe I need to put a 3 there. And now we have a 6 there, and we have 3 sulfurs. All right? We do need to fill in those phases, and I think that's a pretty important step that I tend to gloss over. So let's look at our solubility rules. I'm going to check for nitrates. No nitrates. I'm going to check for group 1 metals. I have one. Rubidium is a group 1 metal. So whatever compound has that group 1 metal is going to be aqueous. Whatever has that group 1 metal is going to be aqueous. All right? Then I've got iron and chlorate. So I will look here. I don't see anything about iron. There's chlorate though, right? So chlorate is going to give us a soluble compound. This will be aqueous. And we can see it over here as well. The rubidium would make it soluble. The chlorate would make it soluble, so it's soluble. It's aqueous. And now I need to find a rule for iron or sulfide, and there's no iron, but there's a sulfide rule. Sulfide will be insoluble unless you're with one of those things, which we're not. None of those things is iron. So this is going to have to be a solid. And so at this point, like if we look back historically, aqueous, 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 solid. Something has changed, it's going to be a reaction. Aqueous, 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 liquid. Something has changed, it's going to be a reaction. Aqueous, 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 aqueous. Nothing has changed, we ended up with no reaction. Aqueous, aqueous, solid, aqueous, something has changed. We do have a reaction taking place, okay? We're going to dissociate all of the aqueous species, separate them into ions. We've got 2 iron ions, and those are 3+. Yes, you need the charge. And we've got then 6 chlorate, ClO3-. I did not identify my pieces. I don't know if anyone cares, but we've got iron and chlorate. I have 2 irons and 2 times 3 chlorates. I have rubidium, not rubidium 2, right? It is rubidium with sulfur. Hold on a moment. All right, that was the dogs barking. Oops. So 6 rubidiums and 3 sulfurs. On this side, I have this. This is a solid, so that's the piece I have. 6 rubidiums, 6 chlorates. This 3 is not affected by this 6 because it is part of the chlorate. I just have 3 of whatever's in that circle. And I think that's a non-trivial skill, is keeping track of like, well, that 2 doesn't get brought down as a subscript, but that 3 gets brought down as a subscript. And the difference is polyatomic ions. You have to be able to spot those polyatomic ions. There's no way around it. We've got 3 times 2 and 3 of our sulfide ions. That's going to give us our iron 2 sulfide and 6 rubidiums. Exciting things must be going on upstairs. All right, we're going to look for our spectators here, and we'll cross out anything that remains unchanged from left to right. If you look here, we have iron ions, and I don't have iron ions. The iron's part of a compound. That's because things have changed, okay? I have chlorate ions, and I have chlorate ions, so those must be spectators. I have rubidium ions and rubidium ions, so those must be spectators. And I have sulfide ions, but no sulfide ions. So my actual reaction must have the Fe3+, and the 3 sulfides, and that's giving us Fe2S3 solid. All right, that is the actual equation taking place. Everything else is just ions, spectator ions, to balance charge. There's a bit of an editing issue there as my family decided to come down thinking they were hilarious to interrupt the video. Let's try this example again. We've got phosphoric acid, H3PO4, and we'll put our parenthesis there for some phases. We're going to try ammonium, NH4OH, ammonium hydroxide, that is a base. We're going to end up with some stuff, but first we need to figure out what pieces we have. So if you look here, phosphate is a piece, hydrogen is a piece. There are 4 oxygens in the phosphate, but there's only 1 phosphate. There are 3 hydrogens, right? Each one of them is a 1+. Ammonium is its own thing, I have 1 of it. Hydroxide is its own thing, I have 1 of it. We would spot this as a double replacement reaction because I have an ionic compound and an ionic compound, and you might know that by the presence of polyatomic ions. That's a pretty good tip-off. If we're looking then at what might replace, or sorry, what we're going to switch where, this hydrogen and this ammonium are the things we're going to be watching. Then we get to the other side. We're going to say the ammonium is now with the phosphate. Ammonium is NH4, it's a 1+. Phosphate is a PO4, that's a 3-, right? So we're going to need 3 of those, and we're going to have some phase there. As we look at the other one, I'm going to have the hydrogen now with the hydroxide. Hydrogen's a 1+. Hydroxide is a 1-. Now, you may recall from this example over here that this HOH is really water, because it is, yeah? It might be easier for balancing purposes for us, though, to keep it as an OH. And oh, look, I just did this a minute ago, all right? Hydrogen we've got, phosphate we've got, ammonium, and hydroxide. Moving this down, we've got 3 of those, 1 of those, 1 of those, 1 of those. Hydrogens, 1, 1, 3, and 1. And you could have separated the hydroxide, it doesn't matter at all. Move here, we have a 3 to balance that out, but that gives us 3 hydroxides. We fix that by putting a 3 there. All right, now we have this reaction. I want to finish identifying our pieces. This is ammonium, it has 4 hydrogens, but I have 3 of it. This is phosphate, it has 4 oxygens, but I have 1 of it. And then here we've got water, all right? We need to look at our phases, and there'll be something mildly interesting taking place. As we look here, my general policy, look for nitrates, no nitrates. Look for group 1 metals. I don't have any group 1 metals, but we'll get back to that in a minute. Look for chlorides, bromides, or iodides. I don't have any of those, so look for other rules. Ammonium, right, makes something aqueous. Sounds like someone just died upstairs. Obviously, it's a busy night. Ammonium is aqueous. And then water, we've already declared, is going to be a liquid. So we will put an L right there. And I think that's super important, so I'll point at it for a while. Just like over here, when you have water, you don't say it's aqueous, because aqueous means in water, and you'd be saying it's in itself. So with the H2O, we're going to say that's liquid, okay? And so these 2 examples are very similar, and hopefully you'll note at the end, we should have the same net ionic equation. So we've got liquid, we've got aqueous, and we've got I don't know. We can look for rules here and say, oh, look, phosphates, those are most likely to be insoluble, but there's a catch, okay? And in fact, I'm going to highlight the space where I'm going to put this in advance. Hydrogen is in group 1 of the periodic table. It's a gas at room temperature. It's a liquid if you get it really cold at high pressure. And maybe it's a solid, right? And if it was a solid, since it is in group 1 on the periodic table, we might expect it to behave like a metal. Now, I say all that with a bit of hand-waving, whether or not I know it's true, but for solubility purposes, we can treat it as a group 1 metal. So, this is in group 1, and we could say, is it a metal? question mark. Now, there was some research recently where a group at a university said they made metallic hydrogen, and nobody was able to duplicate their results, and when somebody came to look at their results, they had lost the sample. So whether or not it happened, I think it's okay for us to say group 1 hydrogen, we're going to treat it like a group 1 metal for solubility purposes, which means this is going to be aqueous, all right? So group 1 metals, and we'll throw hydrogens in there as well in our solubility rules. All right, let's get moving here before my family interrupts again. We have, we have 3 hydrogen ions, aqueous and phosphate, 3 ammoniums, and 3 hydroxides. And we had mentioned previously, but if you screwed up your balancing down here, you'll notice from left to right, because we balanced it here and it was good, so here it should still be balanced. We have 3 of those ammoniums, and 1 of the phosphates, and we have 3 waters, okay? And we'll do that as liquid. So for our net ionic equation, we said, or our complete ionic equation, we would dissociate everything that's aqueous. We did that. Now we're going to look for spectator ions and write a net ionic equation. Spectator ions remain unchanged from reactants to products. Here are hydrogen ions. That and that are not hydrogen ions. That has the hydrogen. It's not hydrogen ions. That is not that. All right, phosphate, ammonium, and hydroxide is not an ion on the other side. So if you look right here, we're ending up with 3H plus and 3 hydroxides, giving us 3 waters. And hopefully you say to yourself, well, if it's a 3, a 3, and a 3, we can reduce that to a 1, a 1, and a 1. So let's do that. I have H plus and OH minus, giving us water. Okay, this is an acid-base neutralization reaction, and it does have the same net ionic equation as the other one. And that is the end of double replacement reactions.